nice introduction. Thanks for the invitation to give a talk here. So I'm very happy. It's my 4th time in Natal, so I'm very happy to give this, an honor to give this colloquium talk. And basically what I'm going to tell you about is about, let's say, perhaps the main research topic in my group, and actually it's the basis of this, is it working? Yes. Of this grant that I got from the ERC, that is one of the best, no, it's the best grant that you can have in Europe for research. And it's related to a scenario for quantum information processing that is called device independent, but also if you want to understand it, and this will be useful for all what I'm going to say, it's a sort of quantum information theory that you, in which you see devices as black boxes. But I will explain all these things during my talk. Okay, good. So let me start by, so I will start assuming that you know a bit about quantum information theory, but not so much. So the first, my first slide is about quantum information theory, or if you want, quantum information processing. What is the field about? So you want to understand what happens when you make this transition. So this transition was, at the level of physics, this transition was understood at the end of 19th century, beginning of 20th century. So people moved from macroscopic scale to the microscopic scale, and they had to invent a new theory that was quantum physics. So now we are doing something similar, but now for information, no longer for physics. We know that when you go to this small atomic scale, you have to use quantum physics, but now we have to we want to understand what happens when you go to this scale for information devices. And when I give this more general colloquium talk, I always say that here I think there is something that is very relevant, at least for me it was something very relevant, because if you had asked me whether to make this transition implies any change in the things you can do with information, I would have said no, okay? Because one of the merits of so I studied information theory, so one of the merits of information theory is that has nothing to do with physics when you study at the university, okay? But actually it's the opposite, okay? So physics has a lot to do with information theory, and in fact, since you change the physical laws that govern your information devices, you can do things that are not possible using classical physics. Okay, so the fact that you change the physical laws that explain your information devices, then it implies that you can do other things. So in particular, we'll have different computers, more powerful, and then this is quantum computer, and then you might have heard of quantum cryptography, that sometimes they say that provides unbreakable security. Okay, so I will focus more about this secure cryptography that comes when using quantum physics, but here is the first message I want to give. So for sure, quantum information theory has implied a change of paradigm in the way we should understand information. Okay, you cannot understand information independently of physics. So I will now, among all these applications, I'm going to focus more on cryptography. So we have quantum cryptography, and often you see sentences like this one. I was even writing this sentence when I was writing papers in the past, and now I try to avoid these sort of claims. But people claim that you have unbreakable information exchange when using quantum physics. So for that, let's try to understand what's the logic of quantum cryptography. I will illustrate that with the first protocol that was invented by Bennett and Brassard, Bennett at IBM, Brassard at Montreal in 1984. It's called BB84 because of that. And the protocol is very simple. I mean, the quantum information theory, what you need to know about quantum physics is very simple. Okay, it's just textbook quantum physics. So what you do is the following, what you want to do in this protocol, you want that Alice and Bob, these are the good friends who want to establish a secret. You want to run a protocol so that at the very end, these two people share what is called a secret key. So a secret key is a list of perfectly correlated bits, so that whenever Alice has a 0, Bob has a 0, whenever Alice has a 1, Bob has a 1, and these bits are only known by Alice and Bob. This is why they are called secret. So now I'm going to tell you how Bennett and Brassard thought about distributing this secret key between Alice and Bob. So at the very beginning, you see Alice is in her location, Bob is in his location, and they don't share anything. So what Alice wants is she wants to send bits, classical bits, to Bob, and she does this by putting this classical information on a spin 1/2 particle. And what she does, whenever she wants to send a 0, she prepares the spin 1/2 particle, let's say with a spin pointing in the plus the direction, or she uses a spin pointing into the x direction. I'm saying things with spin, but you can also use polarized photon. It doesn't really matter. In the same way as bits can be encoded in many different ways, here quantum bits or classical bits encoded in quantum particles can be encoded in different ways. So Alice will, whenever she wants to send a 0, she will send either plus z or plus x, and whenever she wants to send a 1, she will be sending minus z and minus x. Okay, this is sent from Alice. It goes to Bob, and Bob measures in the Z and X bases. Okay, so Alice chooses randomly between these possible preparations, and Bob chooses randomly to measure in the Z or X bases. He uses the same table for reading the information. Now, we all know that if Alice prepares something, let's say pointing in the plus Z direction, and Bob measures in the Z direction, Bob will read plus Z, because when you send a spin pointing in the plus Z direction and measure Z, you will get plus. And he knows that this is a 0, so he will write a 0. But when Bob happens to measure in the basis that was not used by Alice, like here, like Alice sent plus Z and Bob measure X, then we all know that you get a random bit, so no information. So this is bad, but what they can do now, after they run this process many times, Bob announces in which basis he measured, and Alice can say whether Bob should keep this discarded. So they do this. So let's say they discard, in this explanation of the protocol, they discard half of the symbols. And at the very end, they only keep those symbols where Bob happened to measure in the same basis as Alice. So they have perfect agreement between what Alice wanted to send and what Bob measures. Okay, so it looks like the secret key I was telling you about. You see, whenever Alice wanted to send a 0, Bob reads a 0. Whenever Alice wanted to send a 1, Bob has a 1, and so on and so on. Okay, this may look like a secret key, but I didn't say anything about secrecy. This is like a very stupid and complicated way of sending 0s and 1s through the channel. So there is and now, to tell you why it's secret, I have to include the third player in these cryptographic games, which is the enemy, the eavesdropper, that is called Eve. And the problem is that Eve can access to the particles while they fly from Alice to Bob, so she has to read this information. But remember, this information might have encoded into the Z and X basis, and Eve cannot read information encoded in Z and X basis because these bases are not orthogonal. And because of Heisenberg uncertainty principle, you cannot read this information, and this is why the protocol is secure. Okay, that's the first approximation. This is a short course on quantum cryptography. But based on that, you can prove that the protocol is secure, so Eve cannot read this information, so this list of perfectly correlated bits is not only perfectly correlated, but you can prove that it's also secret. Okay? So this is not, I hope you understand the idea. This is just Heisenberg uncertainty principle applied to a very concrete situation. I hope this is clear. I'm not explaining you all the details of quantum cryptography because I don't need to. But what is interesting here is that by making this distribution of spin 1/2 particles, Alice and Bob can establish a secret key, and they can use this secret key to exchange private information in a secure way. And again, also security. So before quantum cryptography, all the cryptography that we use in our computers is based on something called computational security. So we exchange messages, and we believe that these messages are because we believe that to break the protocol, the eavesdropper has to solve a problem that is very hard. Since we believe that the eavesdropper has no computational power to solve this very hard problem, we believe that our protocol is secure. Quantum cryptography is something completely different. So it gives physical security. So the protocol is secure because you believe that the particles that you use for information encoding are quantum particles, so they should obey quantum laws. And the eavesdropper, if the eavesdropper wants to break the protocol, the eavesdropper has to break quantum physics. So our assumption is quantum physics is correct, and then this is why we can prove the security of the protocol. So it's something completely. I'm not saying whether it's better. Well, I think it's better, but it's just different. Okay, very nice. This is a very nice. Years ago, there were some, and also actually, I forgot to say that quantum cryptography is something that you can buy. Okay, so if today you want to secure your messages using quantum cryptography, there are companies that sell you quantum cryptography, so you can use them and you can send messages to your friend using quantum cryptography in a secure way. So this is very nice, but some years ago, there were things. These companies, they bought the devices that were running quantum cryptography. So there were several teams. I think the most active person and best known person in this sort of what I'm going to tell you is Vadim Makarov. So they hacked quantum cryptography. Okay? To the companies, they bought these devices, and they showed that they could break the security of these devices. So you see, this is a picture of Makarov, who is really a quantum hacker. You see that guy here. So this may sound as a surprise, because I was telling you that these schemes are unbreakable. Okay? Of course, they made some noise, because people We were writing papers. These schemes are unbreakable, but then Makarov and his colleagues came and they broke the security. Okay? So how come? So you may believe that I was cheating because I was telling you that the security of the protocol is based on quantum physics. So you may think, which is not the case, that what these people did, they proved that quantum physics was wrong. But of course, this is not what they did. Okay? Otherwise, they would have got the Nobel Prize. So what they did, they just broke the implementation of a protocol. So why? What they broke was the implementation, but not the principle. And the problem comes here. Okay? So this is very important for what I'm going to say. So the problem comes from the fact that when I told you about the protocol, I was telling you many things about theories. I was telling you that the Alice and causing and Bob makes these measurements of spin on the particles. So this is what the theory leaves, and this is where we prove security. Now when you go to a company, the company does not prepare objects living in a Hilbert space of dimension 2. They use lasers. So for sure, a laser does not live in a Hilbert space of dimension 2. Okay? They believe that they are encoding information on a Hilbert space of dimension 2, but you can never be sure about that. I think you can never be sure that you are in only 2 degrees of freedom to encode information. Of course, they don't measure ideal spin 1/2 observables. They have photodetectors to measure this light. So this is where the company produces things, where the provider produces things, and this is where the theories work and where we prove security. So in the end, you end up having a security proof that applies to a situation that does not correspond to the implementation. Okay? So then this is a problem because you live here, you believe that things are secure, but then the hackers live there and they break the protocol. So there is always a mismatch between the theoretical requirements in standard quantum cryptography and what you have in reality. Okay? And because of this mismatch, you can have, there is always the potentiality of having eavesdropping attacks. Okay? So in a way, the fact that you not on the physical details of your devices is a weakness, because if you don't really meet the requirements, the physical requirements of your implementation, you might be in trouble because you have a security, you are relying on a security proof that relies on all these things that are very hard to meet perfectly in practice. And this is related to another problem which is common to quantum cryptography, but also classical cryptography, which is certification. So you may know that about the Snowden affair. So in one of these documents that were released by Snowden, there was, for instance, a particular case where it happened that the National Security Agency of the States, they were supporting the use of a cryptographic solution for some devices. Okay, they were saying, please use this cryptographic solution. Why the National Security Agency was doing that? Because they knew that they could break it. Okay? So of course we don't trust the I don't trust the National Security Agency a lot, okay? So you know that if you are going to use something promoted by the National Security Agency, maybe you don't do that. But the problem is that the National Institute of Standards and Technology, that usually we trust, they certified that the solution proposed by NSA was secure. So they had put a stamp saying, please use it. We certify that it is secure. But it was not. Okay? So this is a problem of certification. And then after they got these papers, they started saying, no, don't use it. We thought it was secure, but it's not. So this is a problem. And this is also a problem for quantum technologies, because if you go to the company selling you quantum cryptography, so you go to them and you say, please give me quantum cryptography. And they tell you, okay, here's quantum cryptography. And you get a box, a device. And then you say to the provider, is this quantum? And the provider will tell you, yes. This is all the certification you get. Okay? So, well, then you say, well, it looks quantum. I don't know. You should put trust on your provider. And sometimes you don't want to do that. And I always use this joke. I mean, my colleagues have seen it many times to explain the situation, which is for the problem of random number generation. And companies also sell you a random number generation based on quantum physics. Again, you go to the provider and you say, please give me a random number generator. And they give you, here's your quantum random number generator. And you say, is this quantum? And they tell you, yes. But this is also a problem for randomness, okay? So there's this cartoon by Dilbert. You see, he goes to a company. Let's say that this is the provider, and he wants a random number generator. And, well, how can you be sure that this is random? You should keep in mind that the probability that a good random number generator gives you this sequence is the same as any other sequence, right? So there's a problem there. And I always use the same example. I'm sorry for people who know me, to explain this problem with randomness. So imagine you have a virtual casino, and you want to have a random number generator to run your virtual casino. You have seen my talk, you know that I can, well, I'm a theorist, but let's assume I'm a quantum experimentalist. You know that I can do things with quantum devices. You come to me and you say, look, I know that you can produce random numbers using quantum physics. I say, yes, I can do that. And then you say, why don't you sell me a device using that? Okay? So indeed, I have the techniques to produce random numbers based on quantum physics. So what I do before you come, I generate many random numbers. I copy them into a classical memory. I put this classical memory into a box. I paint the box with fancy colors. I charge you twice, and I give you this box. Okay? And then you ask, is this quantum? And I say, yes. So you don't trust me, I understand. So you go to your location, and you start generating numbers. And since you don't trust me, you want to see whether these numbers are random. So what are you going to do? You're going to test these numbers using statistical tests. But these numbers are random because I generated them using quantum physics. They will pass all statistical tests. So you say, do you see this guy, Antonio Thin? He's really a nice guy. So you put these random numbers in your virtual casino, and I get all your money. Because the numbers are random to you, but they are not random to me. You see? This is the problem of certification. Okay? And you should trust me. I don't know why you laugh. I mean. Okay, so the solution to that, and this is what the talk is about, is you should think in a different way about devices, and you should think about what I'm telling you. So in my story, I was telling you, you are the user, you go to the provider, and what the provider gives you is a box. Okay? So if you want to make protocols where you don't trust the provider, you should make an information theory that is based on boxes, on black boxes. Hence my title, Quantum Information with Black Boxes. Okay? So for all what I'm going to say, these are our motivations. We want to make an information theory where you don't put any trust. You deal with boxes that you get from the provider, and you self-certify your boxes so that you make sure that they are random or secret or whatever, you name it. But we want a quantum information theory with black boxes, and this is our main motivation because all the problems I was telling you about. Of course, if I want to do a quantum information theory with black boxes, well, these boxes have to allow me to do something with them, okay? Otherwise, I cannot do anything. So what we allow is something, let's say, we give to these boxes the minimal structure possible. What you can do with these boxes, you can give them classical information, and the boxes give you back. And this information, I don't attribute any meaning to this information. So you can here put a symbol that can take n possible values, and as an output, you get r possible results. So I always use the image if you want to think about it. So you go to the provider, you ask a box, and you ask that this box has, say, n buttons. You see these buttons, okay? They are there in the box. And you can press them. Button 1, button 2, button 3. You have n buttons. And whenever you press one of these buttons, at the bottom of the box, there are some lights. And whenever you press one of these buttons, one of the lights is on. And you call light 1, light 2, light 3. Well, I'm just saying buttons and lights. You can think of any possible realization. It can be a knob that you can put in different positions, and then, I don't know, there is a sound coming out of the voice, okay, different notes. It doesn't really matter, okay? What is important is that you can do an action, you can put a classical input into your box, and then you get a classical output. So then, say, Alice and Bob, they go to the provider, they get one of these boxes, and they don't want to put any trust, so they are going to test these boxes. What can they do? What can they do with these boxes? They can spend some time pressing these buttons and looking at the lights. So with that, they can count the frequencies, and they can estimate the probability that this box gives output A and this box gives output B when they press button X and Y. So for that, you don't need to trust the provider. Either you see these frequencies or you don't see them. Okay? So I don't know what's inside the box. This is why we call it device independent. It's independent of what is inside my device. I don't know how the device produces the output given the input. I only want to see these numbers. Whether the box produces these numbers using systems of dimension 2, 3, infinite, I don't care. If I make a protocol based only on these observed correlations, observed statistics, then I'm fine, and I can run the protocol without putting any trust in the provider. Okay? Okay. So in general, we want to do this quantum information theory with black boxes, meaning 2, 3. And the good thing is that you want to certify things only from what we call the observed correlations. So what is the probability that you observe some outputs given some inputs? Okay, so this is I think it's very nice if you can do these things, because you shouldn't trust me. You don't need to trust me. Okay, so it's very good for you, for your virtual casino, if that is possible. And in fact, it is possible, and now I will tell you why it's possible. Okay, why you can black boxes. Before doing that, I want to understand what is the mathematical object we use for that. So, for instance, something that we don't do in this new theory is we don't use Hilbert spaces. It's a quantum information theory without Hilbert spaces. Hilbert spaces are behind the scene. Of course, I'm invoking that these boxes are quantum, so there must be a Hilbert space there. But I don't know what this Hilbert space is, so I cannot use it because I don't know it. I don't want to specify the Hilbert space. So what I'm going to do with is with this vector of probability. So the probability of observing some outputs here, given some input. This is my object, and this is the object I'm going to call correlations. These are the correlations between the boxes, and this is the object I'm going to use for all my information theory. Again, these are quantum correlations. I will assume that these are quantum correlations. So they are produced by means of Hilbert spaces, but I don't know which Hilbert space is used to produce these correlations. So for you to understand, this is, for instance, this vector that I call of correlations. So the first element in this vector is just the probability that I see result 1 here and 1 here when I use input 1 here and input 1 there. Okay, this is the probability. This is a positive number. Then I also have the probability of seeing output 1 here and 2 here, again, when I use input 1 and 1 there, and so on, up to probability of seeing result R here and R there for the same combination of inputs. These are positive numbers, and they are normalized, because these are probabilities. Okay? Normal probabilities. But of course, I have the same situation when I use input 1 and 2 here, and I have the same up to input M and M here. So this is the object that defines my structure. So I'm going to do an information theory with this object. So these are just vector of positive numbers, and they are normalized. So up to this point, the object is too simple to do things. Okay, it's just a probability vector. Well, a joint conditional probability distribution. I have many probabilities here. So I think now here it comes another of my take-home messages. The nice thing is that we are physicists, so we know that these numbers here cannot be arbitrary, but they must obey some physical principles. So these boxes can be any sort of physical boxes, but they are physical boxes, so they cannot violate physical principles. And the nice thing is that physical principles then give limits, give a non-trivial mathematical structure to these objects here. And because of this non-trivial mathematical structure based on physics, I can do an information theory based on these correlations. So let's put some mathematical structure on this based on physics. So there is something I would say that basically we are all going in this room. Okay? So these boxes can do many things, but we believe that they won't allow us to make faster than light communication, because we believe that Einstein causality is true. So by this I mean that if Rafael has a box here in Natal and I go back to Barcelona, I have my box. By doing stuff on my box in Barcelona, I cannot make instantaneously an effect on what Rafael sees. Because if it was the case, me, by pressing buttons in Barcelona, I could transmit information to Rafael. This is just demanding that you see here what Rafael sees. Her probability of outputs given inputs does not depend. It was the case. By changing my input here, I can modify what he sees, and then I could use this to make communication. This is called no signaling principle, so I assume that these nonlinear constraints are satisfied. So when I sum over a subset of the outputs, what the other party sees does not depend on the inputs of the other parties. Okay, very good. So let's say before quantum physics, the way we created was in this way. Okay, so again, think of these boxes. They have been prepared by someone. This person, what this person did with the boxes, this person wrote a program, okay, on the boxes saying how to behave. So you can think of this program. This person put some small demons into the boxes with a piece of paper, instructions, and the instructions were saying, okay, if Alice presses button 3, you give output 4. Okay, just written in the piece of paper. If Alice presses button 2, you give output 7. And every box has a small demon inside the box waiting for the input. And when the demon sees the input, looks at the piece of paper and produces the output. Well, this is an operational way of understanding what are the Einstein, Podolsky, Rosen, local, hidden, variable, model, whatever, you name it, okay? So this is the program is lambda, and in box I, say 1, you produce the output depending on the input the daemon has to produce the output. So these are, I'm going to call it classical correlations, because before quantum physics, I think everyone thought that the only way of producing correlations was by this way. Of course, I am assuming that there is no communication between the boxes, okay? The boxes are on each location, you put the input and you produce the output. And this is just information. This is what one party sees does not depend on what the others are doing. Okay, don't be shy. Okay, but with this, and I'm going to do information theory. So I believe that what you see should be explained by making measurements on each box acting on in a quantum state that is inside the boxes. Okay, so the set of quantum correlations are those numbers that I can write as measurements acting on a state, on a quantum state. Note that here I don't say anything about in which Hilbert space these objects live. So I would say that some numbers are quantum, either exists a Hilbert space where I can define a state and I can define some measurement. Rule, I get this number. Okay, this is my definition of quantum correlations. So what do we know about these sets, classical, quantum, and non-signaling correlations? So a pictorial way of seeing this, if this is the space of correlations, remember, whenever I say correlation, I mean these vectors, okay? So now I fix M, R. This will be a vector of numbers in R, M squared, R squared, okay? So you have many positive numbers here which satisfy some normalization conditions. So in this space, the set of non-signaling correlations is convex, okay? It's here, it's the blue one here. This is a pictorial way, okay? But it defines a convex set. Within the set of non-signaling correlations, we have the convex set of quantum correlation, which is the red one. I'm very bad drawing, but I hope you understand what I'm doing here, okay? So this is the set of quantum correlations, the red one, red-blue, okay? Because quantum correlations don't allow us to make any faster-than-light communication, so there's no instantaneous communication, so it's a subset, but actually it's a strict subset of the set of non-signaling communications. And within the set of correlation, the set of classical correlations appears, which is again convex. So we have classical correlation is strictly smaller than quantum correlation that in turn are strictly smaller than the set of non-signaling correlations. So I'm zooming in this part here. Okay? This is classical, quantum, and non-signaling. So why do we know this? Well, we know that there exist correlations between different devices that do not have a classical explanation. This is Bell's theorem. A bit more. But this is why we know we have this quantum bubble here of quantum correlations that do not have a classical analog. And we also have some results, perhaps less known by the average physics community, is that there are some numbers here that do not allow you to make any instantaneous communication, but do not have a quantum realization. Okay, this was proven in this paper. I will say a bit more about this. So I'm a quantum physicist. I want to do stuff with the numbers here because I believe that my devices are quantum. Okay, so I want to do things about here, and I want to do things beyond classical information theory. So I'm not going to use these numbers here because these numbers here have a classical explanation. So it's impossible that I achieve something that is not possible in classical information theory if I use correlations that have a classical explanation. So if I want to do something interesting, I have to use those quantum correlations that do not have a classical explanation. That is, those quantum correlations that violate Bell's theorem, because then I know for sure that they are not here. So since this is a general talk, I will give but you know quantum physics. Just to make sure that you follow me, hopefully, I will give a very short course on Bell inequalities. Okay. So what is a Bell inequality? I will use it with the simplest Bell inequality, which was invented by Clauser, Horn, Shimoni, Holt. It's called the CHSH Bell inequality. And you see, it's again something that I can explain with boxes, because Bell inequality is nothing but boxes, like the quantum information theory I want to realize. So what is the quantum Bell inequality? You have a source. Source in all what I was telling you about is the provider. So you can think of Alice and Bob going to the provider, which is the source, and getting 2 photons, 2 particles from the provider. So these 2 parties go to their locations, make 2 measurements of 2 results. Well, this is like pressing a button or putting an input on your box and getting an output. Okay, so this is the input, I call it 1 and 2, and the output plus and minus. So what I take is something that is called the CHSH parameter, that is this numbers, this combination of numbers that looks a bit weird, but okay, it has a meaning, as you will see now. So A1 is the output of this box when you press button 1. So it can be plus and minus 1, and B1 is the output of that box when you press button 1. Okay, when y is equal to 1, you will get a plus and minus 1, and this is the number you put here. Well, in classical physics, all these numbers are well defined, so it's plus and minus 1. So what you can see, this is super trivial mathematics, is that this combination of numbers cannot be larger than 2. Okay, so I always put an example just to see how difficult these things are. So if all the numbers are equal to +1, okay, then this is +1 times +1, which is equal to +1. This is +1 times +1, which is equal to +1. +1 times +1 is equal to +1, and +1 times +1, which is to +1, but there is a minus sign, so it gives 2. Okay, so it's not very difficult. Of course, if you take all possible combinations of plus and minus 1, I can tell you, but you can prove it, that this is only +2 and -2. These are the only possible combinations that you can get here. Okay, so this tells you that if things are defined, if the daemon has here, then you cannot go beyond 2. Okay, this is a Bell inequality. Okay, just a constraint on the correlations that you can see. Okay, this is something I construct from the numbers I see, the probabilities I see here, and I know this number cannot be larger than 2. What happens is that if you go to a quantum provider and the quantum provider gives you an entangled state and you make some measurements, okay, you then compute this, but this now A1 and B1 are just matrices, operators living in a quantum, in a Hilbert space. In this case, these are Hilbert space living in dimension 2, and you can get 2 square root of 2. Okay, this is the surprise. This is why you cannot do these things with classical correlations. So if you want to understand the sets I was telling you about, okay, use the CHSH Bell inequality, it's quite simple. So the CHSH Bell inequality is the plane that separates classical correlations from quantum correlations. This is CHSH 2, and classical correlation is below 2. This is what the value is smaller than 2. Quantum correlations give you something larger, and this is why you get something between 2 and 2 square root of 2. This is the part of correlations that have a quantum origin and violate CHSH. And then there is no, you could even get, it can be proven that you could even get 4 for this, okay, without need to send any communication between the parties, because at the moment the theory is quantum physics. But in principle, we don't see any strong okay, you could think of theories giving you 4 without violating faster than light communication. We don't know how to do it, okay, but it's conceivable. And this explains the gap between classical quantum and non-signaling. Okay, so let me just recap. I don't know how much. 25? I still have 25. Okay. So let me just recap what I say. So I gave you some sort of motivation introduction for an information theory with boxes. I was telling you that I want to do an information theory with quantum black boxes. Then I was telling you that the objects needed in this information theory are the correlations between the boxes. And I was telling you that there are 3 physically relevant sets, which are the classical, quantum, and non-signaling. Now, if I want to do an information theory, I have to use this part here, because these are correlations that I know how to achieve with quantum physics. And I know these correlations do not have a classical realization, so I can potentially do things beyond classical information theory. So if I want to do an information theory, I should better understand how to characterize this part. And this is what I'm going to call, I should better. Okay, so I want to understand what's this limit. What are the correlations? What are the correlations I can expect when I make, say, 2 measurements of 2 outputs on 2 quantum particles in any possible Hilbert space? Not can be any possible quantum realization. I want to understand the limits to quantum correlations. I'm giving you a motivation that comes from information theory, but I think this is a fundamental question. So at the moment, our description of nature is based on quantum physics. Even quantum correlations by doing generalization of physics. You change some other things, but not the structure of correlation. So I want to understand what are the possible correlations, possible description of nature, if you want, a more fundamental motivation. Okay, and this is what we did in these papers, together with Miguel, who was, he's still there, poor guy. He knows everything I'm going to tell, he knows better than me, and Stefano Pironio, okay? And the problem is very simple to understand. So imagine you have an experimental lab, you're an experimentalist, but you're a group leader, so you never go to the lab. You just write proposals and give talks. So there is a PhD student, the poor guy spends time in measurements on 2 particles. So the experimentalist is preparing a system, and in this system there are 2 particles that are being prepared, and there are 2 measurements that are implemented with 2 possible results. Spends time getting results, and at the very end of the day, he gets these numbers here. You see, these are probabilities. I can tell you that these numbers sum up to 1. They are positive, so this is something that he can potentially get in the lab. Why not? So the experimentalist gets these numbers, But before going to the professor, he goes to the theories and says, look, with my knowledge of theory, I'm unable to get these numbers. So the theorist says, okay, he's an experimentalist, okay? Well, I mean, he collects the number, and he tries to reproduce these numbers with, say, they believe that they are measuring, say, photons in polarization of photons. So the theory says, okay, I'm going to do this in a moment. He takes Hilbert spaces of dimension 2, and he tries to define a state and measurements so that they give these numbers. He fails. Okay, so the experimentalist goes to the group leader and says, look, I was measuring these numbers, but I don't know how to explain them. And I went to the theories, and he doesn't know either. So the group leader says, what did the theorist do? He was making calculation with qubits and say, okay, go back to the theories and do calculation with dimension 3. So the experiment to the theories fails again. So he goes back to the group leader and says, he failed again. What do we do? And say, try it now with dimension 4. Okay, and the experiment goes and they fail again. So what do you do with that with the situation? I mean, are these numbers weird? Something super relevant, what you are getting? So this is what we want to know. So basically what we want to know is whether these numbers are quantum or not. You see, they look very innocent. These are just numbers, probabilities. So for that, and I want you to understand why this is difficult, okay? Because I want to exclude any possible quantum realization of these numbers. So I want to exclude Hilbert spaces of dimension 2, 3, 4, 5, infinite. I have to run over all possible Hilbert spaces you can think of, all possible states, all possible measurements in these Hilbert spaces. The only constraint is that I assume that I'm making a measurement on one particle, tensor product, another measurement on the other particle. This is the only constraint I'm imposing, because I believe that the two particles are separated. So some years ago, what we did, we developed a method to answer this question. You give me these numbers, and we gave you tools, some tests that are computationally more demanding. It's a hierarchy of tests. And if you give me these numbers, I run the first test, which is the simplest. If you don't pass this test, know this number quantum realization. If I pass, then I have to run the second test, which is more demanding. If I don't pass the test, they don't have. If I pass it, I go to the third, and so on and so on. So the nice thing is that Miguel proved that this is asymptotically convergent. So if something is quantum, you pass all possible tests. If something is not quantum, you will detect the non-quantumness at some final step. So for you to understand what these sets do, they approximate the set of quantum correlations from above. Okay, so I want to know whether something is quantum, whether it's in this set. I don't know how to answer this question. So what I do, I run this test that we found, and then what these tests tell you, they check whether the point is within one of these sets. If the point is not in one of these sets, for sure it's not in quantum. If it's in being, but at the very end, things converge to the quantum set. So again, now the go to the theories, and the theories can use our method and can certify that these points are not quantum. So if these numbers were correct, you would quantum physics in the same way as Bell inequalities disprove classical physics. So there is no quantum way of explaining these numbers. Okay? So either the measurements are not separated, this is one possibility, but if you make sure, because maybe the measurements are space-like separated, define space-like separated event, then if you see these numbers, quantum physics is wrong. Okay, very good. So now we have ways of characterizing this set of quantum correlations. That remember, these were the sets here. Now we know which object we're dealing with, this information theory. And on the way to that, we also provide tools that might be useful for quantum foundations. Okay, so now I will tell you how to make protocols in this scenario. Okay, so remember, you have this casino, and you came to me, and I was giving you this box, and you thought that it was a random number generator, but I knew all the random numbers that were going to be generated by the box, and this is why I was getting all your money. So what you have to do, you have to come to me. You have seen my talk, and you have understood what I'm telling you about, hopefully, and now you have to come to me, and you have to ask me, as a provider, you have to ask me 2 boxes, not 1, 2. And these 2 boxes have to have inputs and outputs. Okay, so you come to me and say, no, give me 2 boxes, and make sure, me, provider, I have to make sure that these boxes violate a Bell inequality. Because if this is something you go back, sometimes pressing box, inequality violation. You remember CHSH? You only need to put inputs and the product. This is something you can do without trusting me. So if I don't prepare boxes that violate a Bell inequality, you give me the boxes back. I cannot cheat you. Either you violate the Bell inequalities and you keep the boxes, or either the boxes that violate a Bell inequality, so you give them back. Now, the good thing is that if the boxes violate a Bell inequality, you know, for instance, in the case of CHSH, that the numbers cannot be predetermined in advance, because if the numbers are predetermined in advance, they are equal to plus and minus 1, and the CHSH Bell inequality cannot be violated. So these numbers are not predetermined, so in particular, I was not able to generate them before you came to my location. Okay, so they are random. So this is the intuition, and actually we can prove that. So we can prove that for any Bell inequality violation, well, you have to believe, I can tell you that for any Bell inequality violation, you can bound the probability I have on your numbers. So you see here, at the point of no, remember the CHSH, the classical bound was 2. At this point, I have perfect predictability. I'm trying to guess your output. Your output takes 2 values. So when I can guess perfectly, my error probability is 0, so my guessing probability is 1. The predictability is smaller than 1, and this means that and actually at the point of maximal Bell violation, which is this 2 square root of 2, the number is perfectly random because you have 1/2. So why do I know that? I know that because I know that this region is impossible within quantum physics. And why do I know that? Because I have tools to characterize. So you have to come to me, and you have to ask a box that violates a Bell inequality, and then you use this curve to bound the predictability, and from that you can generate good random numbers. I'm not going to tell you this. Okay, so we can establish links between the Bell inequality and the randomness of your devices only from a box test. Okay, so well, this is what I was saying. Okay, this I think I can skip, but also we have ways of doing a quantum key distribution using device independent. Okay, so I can tell you about this device independent because I think it's for some applications, it's a very nice way of thinking about devices, okay? Especially if you want to do, again, an information theory against a non-trusted provider, you better think about boxes. But I think this is also, it gives you nice tools to consider other questions in physics. So let's say, on quantum correlations, this is relevant for quantum foundations. We have some results on that. I think it's a nice problem also from a quantum optical point of view because this to implement this protocol is not easy. You need a proper Bell violation. I'm not going to say that. So I'm going to tell you more about some of the results we got using this approach for many-body physics. Okay. So among all these 4 topics, I'm going to focus on that one. I'll tell you about some results that go more into the line of applying these techniques, dealing with these correlations in many-body systems. Some of the results that we got in this direction. So the first result is something that we did, so Belen was also involved in this, she's sitting there, and it's a collaboration together with a group of Maciek Levenstein at ICFOT and Tamás Vertesi from Debrecen, Hungary. So here, what we wanted to know is whether we can detect a Bell violation in a, say, big many-body quantum system. So the question is, it's a bit, okay, here I will try to put it in a non-formal way. So what we want to see is whether natural, I'm not defining what natural is, but let's say some sort of natural many-body quantum state, you can see a violation of Bell inequality when making natural measurements. And natural measurements in this context is going to be, you measure 2-body correlation functions, which is something quite standard in a many-body context. Okay? From a quantum information theory point of view, it's like, okay, if I have a system made of many particles, and you give me, say, the weakest form of correlation, which is just represented by the correlation between pairs of particles, I want to know whether I can, only with this information, I can sometimes check whether this big system violates a Bell inequality or not. And what we proved that this is possible. Okay, so for me, honestly, I didn't have any intuition about this. So whether two-body correlation functions are enough to detect, say, the strongest form of non-locality, which is a Bell inequality violation, it was open, and we proved that this is the case. Okay, so we could construct Bell inequalities for a many-body system. Okay, a bit of the idea of the inequality. So the inequality, remember, in the Bell inequality, we take the simplest case, so you make two measurements of two outputs that I will call plus and minus 1, and the observables are, so it's a Bell inequality for n systems, okay? So you have the sum goes from 1 to n, and I only take symmetrized observables. So this is the sum of measurement 1 in party 1, measurement 1 in party 2, measurement 1 in party 3, and so on and so on. I sum all these outputs. Okay, well, maybe what is relevant here is that, okay, we got some inequalities. The details are not so important, but what is relevant is that when you compute the quantum violation of this Bell inequality, remember what we now becomes an operator, so this S1 becomes the sum of the okay, you see here, when you sum sigma x on all particles, this is of the global spin of the big system. And here, when we are taking just product of two measurements, this is a two-body correlation function. So the nice thing, quality making computing moments of first and second order. This is why this Bell inequality is nice for experimentalists. What we did in this part, we studied Bell inequalities made of two-body correlation functions. We derived some of them, and we showed that, for instance, weak states that are ground state of some okay, I don't remember for some many-body systems, you can find ground state that violates these Bell inequalities. So we're happy by this result. We also made a presentation. So we thought now it would be nice to make the experiment. So we talked to experimentalists because we thought that it would be implemented. But we were not fast enough. But another group took our paper and the theory, they understood it, and they made the experiment. So they made a demonstration of Bell inequality violation with a Bose-Einstein condensate made of 480 particles. Okay, so they made, so they could prove that there is a violation using our inequalities. We're a bit slow for that. Okay. So how much? Okay, good. Anyways. Second result I wanted to tell you is now I'm going to tell you how you can also measure, you see, because I want to make this information theory with black boxes, I like very much Bell inequalities, so now I'm telling you about things on Bell inequalities with many body states. Okay? So now that's another project we had, now it was again with Maciek and with Ignacio Cirac. So we wanted to understand how you can measure a possible Bell inequality violation just by making an energy measurement. Okay? This is not a proper Bell test, because when you measure energy, you measure a global observable. This is not a Bell test, okay? But you want to infer properties of your system just by measuring energy. And the idea is simple, so I will represent with this rather standard many-body Hamiltonian. Okay, this doesn't work, but it's useful to illustrate my idea. Okay, so imagine you have this standard many-body Hamiltonian, so you have sigma x on particle I, tensor sigma x on the neighbor. It's a 1D system with possibly one asymmetry here. So what I want to do, I want to interpret this Hamiltonian as a Bell inequality. So maybe you remember what I did for CHSH. I had this classical expression with number, A1, B1, plus A1, B2. And what I did, I replaced these numbers by operators. Now I want to do the opposite. I want to start from operators, and I want to replace them by numbers. Okay, so instead of starting from the Bell inequality and going to the Bell operator, so I replace numbers by operators, I want to start by an operator, and I want to interpret this operator as a Bell inequality. So I will replace the operators by numbers. So this is what I do. I just take this operator and put a number. I call plus and minus 1, because I spin 1/2 particle. But this is now a Bell inequality. You can, I don't know why I made a typo. You can even remove here the tensor product. This is just the product of two numbers. So what is the Bell inequality? I have to maximize this expression, which is just a value that depends on plus and minus 1s, over all possible assignments of plus and minus 1. So you can see this classical spin system, and I want to find the ground state spin system. It's the same. Okay, I have to vary over plus or minus 1 and find the minimum of this quantity, which would be the ground state energy configuration. Now, if this number happens to be larger than the ground state energy of this, then the ground state of this system violates this. I can think of this as a Bell inequality. I replace the numbers by operators, and I know that there is a state whose energy gives a number smaller than the. I hope you understand, because I think it's pretty simple. Okay. So this is a good idea. Okay, I think. Now you have to see whether it works. Okay, because it's nice, but you have to see whether it gives you something relevant. So the nice thing also is easy. So you can run to find the ground state of find the ground state energy of classical systems with local interactions. So what the only thing we have to do is we have to take a quantum Hamiltonian. We have to make this trick, replace operators by numbers, compute the ground state energy of this system using this dynamic, and then one system. So you can use Jordan, you can use density matrix randomization group. There are techniques to compute the ground state energy of 1D system. This is not so difficult when you have local interactions. So, but this is the main idea, okay? So usually computing a ground state energy is difficult, but for classical 1D systems you can do it, and for quantum systems, sometimes you can do it if you take systems that you can solve with Jordan-Wigner, and if not, you can also use some methods based on matrix product state on the matrix randomization group, which is the same. So we found some cases, some sort of spin systems with random couplings, where we could see that the quantum value is on the classical value, and that you could understand as a violation of a Bell inequality. Okay, and the last thing I want to tell you about is like another last paper. This is now together with, I'm not sure if he's here, maybe he skipped my talk. Very good, I like him a lot. So this is a paper that, that was in my group together with Flavio, Danny, and Peter. And basically here, it was a quantum information problem. So imagine you, but I think it might be useful also for many-body experiments. So you have a many-body experiment, say a lattice, an ultra-cold system where you have a system of many particles, and you want to prove whether this system is entangled. Well, this is very because there are many particles and the dimension grows exponentially. So we want to find something that is efficient. And the idea is, again, I think it's so again, when you go to the lab, at the end of the day, what you measure are just the probabilities. Okay, so imagine you make different measurements on your particles, you get different results, and you have some probabilities. They don't need to be sufficient to reconstruct the quantum state. You just make some possible measurements on your system, and you get some possible outputs, and you measure these probabilities, these correlations among the particles. So I want to know whether these correlations are compatible with are only compatible with an entangled state or not. Because if they are only compatible with an entangled state, I can certify that a many-body system is entangled. So if something, if some correlations don't violate a Bell inequality, okay, for sure. If they violate a Bell inequality, for sure the system is entangled. But if they don't violate a Bell inequality, I know that these correlations can be written as local measurements acting on the quantum state because they are quantum correlations. But on top of that, I know that these measurements commute. So everything is classical, so I can write them as commuting measurements acting on my quantum state. So if these numbers are quantum, they can be written in this form. If these numbers have a classical explanation, they can be written in this form. But moreover, I can find situations where these measurements commute because they are classical, have a classical explanation. So I was telling you that we have this, we designed in the past, some years, 10 years ago, we designed a method to answer this question, whether some numbers were quantum. Now we only, and this was the picture I was telling you about. So now I only have to solve the same problem, but on top of that, imposing that my measurements locally commute. So everything commutes now here, and this is why they are classical. And actually, the structure is very similar to what we had. I can impose this constraint. And now I'm not testing against quantum physics, but I'm testing against classical physics because I impose that everything commutes. And in classical physics, everything commutes. If you want to understand that, this is the set of classical correlations. Now okay, sorry, this should be the C that I was using before. Now it's L because of local, but it's the C that I had before. Again, what this hierarchy does, it approximates the classical set from above. In the same way as before, I was approximating the quantum set from above. So just to summarize the idea of the method, so we know that it's some correlation of violet and Bell inequality. I can write them as quantum commuting measurements on a quantum state, and then I can use the method I had before, just make some, adapt it a bit, and then I can do the same, apply the same machinery. So as an application of the method, we took some paradigmatic examples of any qubit states in quantum information theory. One is this is a decay state with one excitation, or W state, or you name it. I mean, this is just a symmetric state of one photon or one excitation. So what we saw here is that on our test, our method arrives up to 29 qubits. Okay, so we can, if you had a system made of 29 particles and you make this measurement, with our method you can prove that the state is entangled. But it's possible making a brute force approach. And we saying that the techniques that we have to characterize the structure of quantum correlations, you can also adapt them to understand whether a big system is entangled, and it works reasonably well. Okay, with this, I'm arriving to the conclusions because it was long. So let me just summarize. So I started telling you about an information theory with black boxes. This is what I call, and the reason I was giving you is because in many situations, cryptographic applications, you go to the provider. You don't want to trust the provider because the provider can cheat you, or maybe it doesn't cheat you, but just makes mistakes that are not under his control. So for that, we need an theory made of boxes, and for that, you need boxes that violate Bell inequalities. Because if some boxes don't violate any Bell inequality, you can never be sure if these boxes are quantum. The only way of certifying that some boxes are quantum is if they violate. So it's an information theory based on Bell inequalities. Then I briefly told you, I gave you tools to make information theory based on these boxes, and I briefly told you about how to make protocols for knowledge generation and secure key distribution. Now, I didn't mention, but I think it's relevant for the discussion, is that the implementation of these protocols is challenging. So already, the implementation of standard quantum information protocols is challenging. The implementation of these protocols is even more challenging. It's possible, but it's challenging. So I think it's an interesting problem. We are working on that. So for instance, we recently realized that the use of single photons might be promising to realize these protocols. Okay, I didn't say anything. I just want for you to remember that the implementation of these protocols is challenging. And I was trying to tell you that I think this way of thinking provides an alternative insight into quantum physics, and since quantum physics appears everywhere, also in some physical problems. So I briefly told you about quantum foundations. So we have methods to disprove quantum physics. And I also told you that how you can use these methods to shed light, that's to detect the Bell inequality violation in many-body physics. And let me just conclude with a very general remark. I think this sort of approach is relevant. I mean, if quantum technologies happen to become real, so these approaches. Again, we'll need things to certify that applications are quantum. Because again, if quantum technology is pure technology, you will go to the provider and you will want to make sure that things are quantum, okay? Because you don't want to go to the provider and say, is this quantum? And say, yes. You want to have the tools to certify that the devices are quantum. And more in general, you want to know whether some quantum devices are random, secret, a quantum computer, entangled, and so on. And this is why this I conclude. Thank you very much.